My name is Christian, and this is my complete explanation for the fluid pressure and manometer homework from Chapter 12. I'll be covering every part A through G using equations from the textbook and showing how to solve each one in detail. The topics in this chapter includes absolute pressure, gauge pressure, and using manometers with fluids like water, oil, gasoline, and mercury. This will be specifically key example variation problem 12.4, and I'm going to start off with part A. Give me a second, my pen's not working. There you go. We're going to start off with part A. It states liquefied natural gas, LNG, in a vertical tank storage tank has a density of 455 kilograms per meters cubed. The depth of LNG in the tank is 2.00 meters, and the absolute pressure of the air inside the tank above the upper surface of the LNG is 1.22 times 10 to the fifth power PA. What is the absolute pressure at the bottom of the tank? Okay, so we're given vertical LNG tank with a fluid density of 455 kilograms per meter squared and a depth of 2.00 meters. All right. And the atmospheric pressure above the LNG is 1.22 times 10 to the fifth power PA. These are all given to us, and we'll use these to solve the problem. The equation for this is P equals PATM plus PGH. Well, this is like Roman or Greek, um, a Roman or Greek symbol, but PATM is the pressure of the air above the fluid. This is the pressure due to the fluid column, and this will give you the absolute pressure at the tank's bottom. Now we know this, we're just going to substitute values that they gave us. 10.5 plus 455, 9.81, 2.00, and that'll equal 1.22 times 10 power plus 8, 922.9, and then that will equal 1.31 times 10 to the fifth power PA. Okay, that's for A. Now we're going on to step B. Here we are let me read it out first. You fill a vertical glass tube to a depth of 15 centimeters with fresh water. You then pour on top of water an additional 15.0 centimeters of gasoline. Density is 7.40 times 10 to the second power kg over meter squared, which does not mix with water. The upper surface of the gasoline is exposed to air. Find the gauge pressure at the interface between the gasoline and water. Okay, here we are simply finding the gauge pressure at the interface between gauge and water. I'm going to write down what we know. We do know that P, a gas, pressure of gas is 740 kg per meter squared. I mean cubed. My bad. I think I keep saying squared. And we know the depth or the height. Yeah, the height would be 15.0 centimeters, but you got to convert that into 0.15 meters. The equation we're working with today is going to be P equals PGH. Again, we went over this. PGH is the pressure due to the fluid column. Um, and then we're just going to plug what we know already. So that would be P equals 740 times 9.81 times 0.15, which would equal 1089.9, rounded up 1090 PA. Do not forget your units. Okay, we're going on to C now. Now we need the total gauge. Okay. Let me read it again. Find the gauge pressure at the bottom of the tube. So here we need to find the total gauge pressure at the bottom, and that's the pressure that would be from the gasoline and water combined. So with this, we know that we have to use this equation. P equals P1 GH1 plus P1 GH2. Because this is pretty much, this is gasoline, and this is water. That's why it's separated by two different numbers. And we do know the values of this. So gasoline, its P equals 740 because we did it in the problem before, and its height is 0.15. And then for water, that is P equals 1,000, and then H would equal 0.15. We got this. Yep, we got this. Oh yeah, yeah. That's from the last one. So so now we're going to just calculate what we know. So that would be P equals 740 times 9.81 times 0.15 plus 1,000 times 9.81. Let me clean that up. 9.81 times 0.15, and that should be set to equal 1089.9 plus 1471.5, and that should be approximately 2560 PA. Let me clean that up. These are the two pressure contributions. They're added together because they're stacked. Okay, now on to part D. Part D is asking us in an open tube manometer, see the figure below. The absolute pressure in the container of the gas on the left is 2.10 times 10 to the fifth power PA. If atmospheric pressure is 1.01 times 10 to the fifth power PA, and the liquid in the manometer is mercury, density is 1.36 times 10 to the fourth power kilograms over meter squared. What will the difference in the heights of the left and right columns of the liquid be? Express your answer in correct units. Okay, now we're using an open tube manometer. The gas on the left has a pressure of 2.10 times 10 to the fifth power PA, and the has right is exposed to air, which would be 1.01 times 10 to the fifth power PA. We know this because that's the basic one for air. And then mercury will equal P equals 13. That's what mercury will equal. And our goal is to find the height difference between arms. So that would just be the change in P. Equals PGH. To find this, we're just going to solve for H. So we're just going to rearrange the equation. Okay, change in P equals 2.10 to the fifth power minus 1.01 times 10 to the fifth power. That will equal out you with 10 point, what? That will equal 1.09 times 10 to the fifth power. Then you put that for H. That'll be 1.09 times 10 to the fifth power all over that. And then that will equal 18 millimeters. We found out that this was mercury, and we just it left it as a density of like this. So we just solved it or made it a real like number, so we could plug it in, and it'll just come out a little bit easier for the problem. That's the only reason we did that. Now on to part E. E is saying in the manometer tube shown in the figure below, I'm just gonna draw it for you. Manometer tube, uh, shown in the figure below. The oil in the right-hand arm is olive oil of density 916 kilograms per meter squared. Gonna make a very hasty drawing of this. Oh, you got like little dots over here too. Yeah, I wish I could pull up a picture, but I can't. Um, so this is what it looks like pretty much. And this is A of oil, height of oil. And then this also says H water. And then this is P water. I'm just gonna put P that, and then this one is P oil. Okay, just gonna cut off like right there. That's what the manometer tube looks like. Um, I don't know what planet this manometer tube is from, but it's not from Earth's origin. Um, Pretty much, if the top of the oil is 25 centimeters above the tube, what is the height of the water above the bottom of the tube? Now we're going to be comparing both sides of this YouTube. That's a good one, right? Oil on the right is, this is what that equals out to be. 916 kilograms per meter cubed. And water is on the left. This is what we know. We know the height of the oil. Know the height of the oil equals 25 centimeters, right? And we know the pressure of the water is 1,000. We know this because it was stated. Um, so we're just going to use this equation. P water, G H water. So this is like, let me show you. This is like this. This is basically this base equation that we found at the start. It's just replaced with water. And then we're going to just make it set it equal to P oil, GH oil. And then we're just going to solve for the height of water by just rearranging. So P oil over P water times height of oil. With that, we know that the P of oil is 916, and we know the bottom is going to be 1,000 for water because it's right here. This is right here. This is right here. This is given to us. So we're just going to plug in times 25 equals 22.9 centimeters. So this would keep the pressure balanced across the tube. Okay, now we're on to one of the final parts, which is part F. Read out for you. What is the gauge pressure of 15 centimeters beneath the surface of water? Express your answer in appropriate units. Okay, now we're just going to calculate the gauge pressure 15 centimeters below water. So instead of 25 centimeters here, we're going to do pressure equals PGH, which would equal 1,000 times 9.81, because that's gravity, 0.15, because we just converted this to meters. That's how we got that number. All right. So with that, that would equal 1470 PA. This is just like the diving pressure problem, and it's very standard. We did not have to rearrange any equations. We just had to know the equation, and once you know the equation and the numbers, then that's all you need. Okay, now we're going to see for our final question is at what depth below the surface of the oil is the gauge pressure the same as part F? Express your answers in correct units. All right, so we're just going to rearrange. H equals P over PG, which would equal 1470. So that's basically what we just found. All over 916 times 9.81. Let me calculate that real quick. That'll equal 16.4 centimeters. And with that, that concludes my explanation of the full homework set, parts A through G. I use fluid pressure principles and manometer concepts with step-by-step equations. Feel free to leave a comment if you don't agree with any of the equations or how I did this exam. But hope you have a wonderful day and thank you for everything this year. I don't know if this is going to be the last examination. I don't know if you said the next two are written, but if this is the last video you see of me, then hope you have a great rest of your year. And yeah, that's all.